In this example, we have a Rankine cycle that has superheat, which means that the vapor entering the first stage turbine is a superheated vapor, and it has reheat. So we have two turbine stages, and the working fluid, in this case water, is reheated between those two turbine stages. So we're told that superheated steam enters the first turbine stage at 10 megapascal. So we can just go ahead and denote that on our diagram. And it expands to 1 megapascal through the first turbine. Okay. And then it's reheated to 500 degrees C. So that will be the temperature at state 3. And then it expands through the second turbine to a pressure of 6 kilopascals. The turbines are ideal, but the pump is not. It has an isentropic efficiency of 87%. So we're asked to determine the net work per unit mass flowing into the first stage turbine, the heat addition per unit mass entering the first stage turbine, so that will be Q dot N, and the thermal efficiency of the cycle. So you may be tempted now to go over here and draw this TS diagram. I am going to hold off doing that until our states are defined, and I hope you'll see why. Okay, so now let's look at state number 1. So we know that the pressure is 10 megapascal, and the temperature is 500 C. Okay. At state 2, my pressure is 1 megapascal, and my temperature is unknown. But I do know that because my turbine is ideal, that the entropy at state 2 will be that at state 1. At state 3, my pressure is still 1 MPa. My temperature is 500 C. So it will be easy to pull out an enthalpy value from the table for that one. At state 4, I know that the pressure is 6 kilopascal. And I really, at this point, don't know much more about it than that. Of course, my turbine is ideal, so S4 is equal to S3. But I don't know if that's going to be a saturated mixture or a saturated vapor or maybe even a superheated vapor. Okay, at state 5, my pressure has not changed from 4. And I also know that I want a saturated liquid entering the pump. All right, at state 6, I will have compressed that liquid back up to the boiler pressure of 10 megapascal. And now I've got a compressed liquid. Okay, so let's go back up to 1. So this is a superheated vapor at 10 megapascals and 500 C. This is a value easily pulled from the table, no interpolation needed. 3375.1 kilojoules per kilogram. And the entropy is 6.600 kilojoules per kilogram Kelvin. Okay, so then using that bit of information, I can now go to my 1 megapascal block in my superheated table, okay? And so you kind of have to guess at this point whether or not it's going to be superheated or a saturated mixture, what have you. But an educated guess would be maybe pressure number 2, or state number 2, is a superheated vapor. So I go to the 1 megapascal block, and I find that between the temperatures of 200 degrees Celsius and my saturation temperature, my entropy lies within that range. And so I can use that knowledge to interpolate between those two rows and find H2. So I'll write down the values of those, and I encourage you to go into the tables and see where these come from. But again, the 1 megapascal block of the superheated steam table. So the first value, 28.3, is the enthalpy at 200 degrees Celsius, and the 2777.1 is the enthalpy at the saturation temperature. And here is S2, 6.600, and then again the entropy at the saturation temperature and the entropy at 200 Celsius. Okay, and when I solve this, I find that H2 is equal to 2779.1. Okay, so I'll go back, write that up here. Okay. So again, point 3, if point 2 is superheated, when I heat something superheated, it will definitely be superheated. So I'm just going to go to the 500 degree C row in the 1 megapascal block of my superheated steam table and pull out my entropy and enthalpy. Okay, so now armed with S3, I know S3 and S4 are the same. So if I now go to my saturation table at 6 kilopascals, so I look in this row, I'll find that 7.764 lies between the entropy of a saturated liquid and a saturated vapor. So I know that I have a saturated mixture at state 4. And like I did before, I can use interpolation to find H4. So maybe you think about finding a quality. So the quality of my saturated mixture is equal to that. That should look familiar. And it's also equal to S4 minus SF over SG minus SF. And so now what I'm going to do is just eliminate the middle step here and equate this ratio of enthalpies to this ratio of entropies to find what I'm looking for, in this case, H4. So H4 minus 151.5. Note that this is actually going to be this is the enthalpy of the saturated liquid at 6 kilopascals, which means it's also equal to H5. Okay. And then now the difference between the enthalpy of a saturated liquid and a saturated vapor, 2415.1. This is often referred to as HFG, and it is in your table. Okay, so now just plug in my entropy values. And this gives me an entropy at 4 of 2240.3. Okay. All right, so now let's look at 6. So my pump is not ideal. So I can find H6S first. So that would be, let's first treat the pump as ideal and then apply our isentropic pump efficiency. So if the pump were ideal, as we've seen in past examples and lectures, H6S minus H5, so that change in enthalpy through the pump is equal to V5 P6 minus P5. So H6S is equal to H5 plus V dP. And again, I want to convert all pressures into kilopascals, and that will give me kilojoules per kilogram when I multiply it times my specific volume. So here I've got 10,000 kilopascals, that's my 10 megapascals, and then minus 6 kilopascals. And that gives me an enthalpy for H6S of 161.6 kilojoules per kilogram. And now I can apply my equation for the isentropic pump efficiency to find the true H6. So 87%. So therefore, H6 is going to be equal to H5 plus H6S minus H5 over eta P. And just for the sake of neatness, I'm omitting my units here. All right, and that gives me an enthalpy of 163.1 kilojoules per kilogram. All right, we'll scroll up and fill that in. H6, 163.1. Okay, so now I have an enthalpy at every state in my cycle. So now the world's my oyster. I can really calculate anything that I'm asked to. Before we do that, let's go ahead and draw this cycle on a TS diagram. Okay, so the first thing we need to do is pop on some isobars. So I'll do this in red, and there'll be 3 isobars. There's going to be a 10 megapascal isobar. Right under that, I'm going to do a 1 megapascal isobar, and then down here, much lower pressure, 6 kilopascal isobar. Okay, so I'm going to draw this process line first. Oh, let's do this in black. Okay, and you'll see why I'm doing that in a second. All right, so I'm starting at 1, which is a superheated vapor. Okay, and I'm expanding down to 2, which is still a superheated vapor, and then I'm reheating to 3, which is at the same, it needs to be at the same temperature as 1, all right? So T1 is equal to T3. So look here, the way that I've done my diagram, that's not actually the case. So let's do a reset. This one can get pretty tricky. Okay. All right, so let's be a little bit more conservative with where we put number 1. Okay, so come down and then back up, same temperature, and then down. All right, so here we got 1, we've got 2 and 3. Those are at the same pressure. Okay, and 1 and 3 being at the same temperature. And then we come down to 4, which is our saturated mixture. And then we're going to cool on the condenser over to 5. Okay, and then finally in the pump we're going to compress all the way up to 6 at my highest pressure, 10 megapascal. Okay, just a few more labels on here for pressure. Okay. All right, so now I can start knocking off A, B, and C. So in A, I'm asked to find the net work per unit mass that enters the turbine. So what that is asking me for is W dot net over M dot. Okay, and you'll notice that we weren't given M dot in the problem statement. So W dot net is the work that's being done by my first turbine plus the work that's being done by my second turbine minus the work that I have to put into the pump, and then all that over M dot. Okay, so each one of these quantities over M dot is just a difference in the enthalpy. All right, so I've got for the first turbine H1 minus H2. For the second one, H3 minus H4. And finally, the work I'm putting into the pump, H6 minus H5. And I'll spare you all the details of me plugging and chugging there, but I'm going to expect an answer that has the same units of enthalpy. And when you plug in the enthalpies that we got above, you have 1823.2 kilojoules per kilogram. All right. And next, we're asked for the heat transfer into the fluid in the boiler per unit mass flow rate. So I need to look at the heat that's entering my fluid between states 1 and 6. And the heat that's entering the fluid between states 2 and 3 in the reheat portion of the cycle. Okay. So again, I'll spare you the details of plugging and chugging, but that gives me 3912 kilojoules per kilogram. So in part C, I'm asked to find the thermal efficiency, which is W dot net over Q dot N. It's what we want over what we give. And so I can divide by M dot on the top and the bottom of that ratio so that I can use the values that I have from above. And so again, thermal efficiency is not a function of mass flow rate. And that gives me a thermal efficiency of 0.466 or 46.6%.